In this video, we are going to begin our discussion of section 4.7. This is called reduction of order. We're actually not going to hit the method until the second half of this video. So we are going to extend most of our theories now to higher order differential equations. So we're going to see a lot of this. Oops, that's not my highlighter. A lot like this. Nth power, no longer just a second. We are going to apply the superposition principle here. What this says is that if I have two solutions to a homogeneous linear ODE, let's remind yourselves of what homogeneous means. Homogeneous means that this g of x would be equal to 0. If both of those are homogeneous, then we have a new solution where we can take C1 and C2, new constants, and multiply them by each of those solutions and add them together to make a new solution. This is also something you're going to apply later in linear algebra. You're going to see this a whole lot moving forward, this type of built equation. That's for homogeneous linear ODEs. That's when that g of x equals 0. Non-homogeneous, the next ones, are when the g of x equals something else. And this is what we're going to apply in our next example. And we're going to extend this idea to a generic idea that we're going to apply to the rest of the semester, really, up until the last unit. I don't want you to be too thrown off from this. I haven't really shown you guys this. This is like operator form, and I just don't focus on it. This is like your DE. It's just the left side, the left-hand side of that DE of this form. There's a way we can call this left-hand side over here. It's like the operator on Y, linear operator on Y, and that's what we have there. Don't focus too much on it. It's just the left-hand side. Okay, so this says the left-hand side y has a solution when that right-hand side equals g of 1. That solution is y p1. Don't let the sub-indices throw you off. It's just y, and the p is a particular solution. That's what p stands for. And then the 1 is our first one. Okay, and it goes with g1. Then we also have an equation, the same left-handed side, ly, equals a different right-handed side, g2, and it has its own solution, y sub p sub 2. Particular solution, the second solution. They said if that happens, then if I take that same left-hand side and I take the first right-hand side and the second right-hand side, that should be a g. Sorry for the typo there. A g. There we go. So if I take those other solutions, then I can take a constant, two constants, and have a new solution. That will be my new DE. The new DE would have a right-handed side built out of this and a constant plus this and a constant. That's what this is saying. The same DE equal to that. Our particular solution takes that same C1 and same C2 that's in the rest of that, and then multiplies them by their associated solutions. Like G1 would be multiplied by C1, so we take y sub p sub 1, multiply it by C1, and then we add it to C2 times the second solution. So we can apply it in that way. We're going to see that here. Let me erase all this chicken scratch on here. I haven't heard that expression in a while. Okay, let's take a look at this and apply. We're going to apply the superposition principle for non-homogeneous linear ODEs here. Okay, so they say, okay, take this DE, so let's note that this left-hand side looks like that, and they say, okay, that's going to equal 6x squared plus 2, has the solution that. Okay, those go together, right? That right-handed side, 6x squared plus 2, goes with what I have boxed off there, also in this weird orange color. Okay, notice here, they say the same left-handed side DE, and now it's equal to negative 12 e to the 3x, has its own solution, and that's that solution. And now they're asking, if we have that, is it possible to use those to find the solution of this DE? Now, what I want you to notice is the left-hand side is exactly the same, except for there's a typo, there should be a prime. All right, so the same left-handed side. So I'm going to try to set this up to match what they're saying. They're saying then we should be able to take some constant times G1, take some other constant and times by G2, remember that's a typo, G2 there, and have a new solution. So if I can rewrite my DE that way, then we'll be on the right track. So let's give that a shot. Let me pick a color that I haven't used on a box or anything. So we're going to write y prime, double prime, minus 6y prime plus 9y. And what I'm going to try to do is write C1 equals that brown solution, 6x squared plus 2, plus C2 times the blue one, the negative 12 e to the 3x. They're saying if these two things, if we can find a C1 and C2, then we can find a new solution. Okay, well, if you can tell, this kind of matches that, and that other one matches that, right? These two expressions here. So I'm going to write those out. C1 times 6x squared plus 2 equals 3x squared plus 1. Okay, I'm trying to match that. I'm going to just consider C1. I need 6 to be a 3, so I think C1 is 1/2, and that matches with that 2 as well. Right? We can also take C2 times negative 12 e to the 3x. We want that to be a 24 e to the 3x. Well, that means C has to be a negative 2. What this tells me now is I have a y sub p, we'll call that my particular solution, not the 1 and 2, but this new one. I guess I could call it 3. Let's do 3. Y sub p sub 3 is 1/2, because that was C1, times y sub p sub 1, minus 2 times y sub p sub 2. And we would just plug those in. Let's do that. Y sub p sub 3, and that's 1/2 times 2/3, 2/3, x squared, 8/9 x, plus 2/3, minus 2 times negative 12 e to the 3x, and I'm good with you stopping there. That's a fantastic answer. There is a level of not completely evaluating your expressions that I'm totally okay with. Once you get to a point that it's just algebra, I'm cool with you stopping. I do want to see this step to this step because you are showing me that you know what those are. I know it seems silly, but you're completing it. But once we go from here, unless some crazy, like we go from this crazy trig expression down to the answer is 4, right? We don't really need to go that far. You can just stop there. That's a perfect place to stop. All right, so that's what that superposition principle is saying. We're going to be using this a lot moving forward. Let's apply this in a different way. All right, here's a general solution of an nth order homogeneous. Remember, homogeneous is when the right side of that nth order linear ODE, the right side is a 0. So what they're saying here is if I have a bunch of solutions, y sub 1, y sub 2, up through y sub n, then I would have a whole solution there, y equals that. Now, what they mean by general, just in case, and we mentioned this up front at the top of the class of the semester, general solution means it covers all solutions. So I can actually find nth, since it's an nth order, I can find n solutions and then stack them like that with that in a linear fashion there. Right, multiplied by each a new constant and then added together. Now, why this is great is we can find that, and really we should call, when we have something like this, sometimes we'll call it the y sub c. And this is due to this. This is called the corresponding homogeneous solution. And what this means is if I take a DE, right, let's say I have a DE here, and it's like some left-hand side, right? And let's get used to this y thing. Remember, that's just an operator. It just means left-hand side. And let's say it is equal to like some function of x, g of x, and it's not 0. We can actually consider the solution. This is the corresponding homogeneous dE. Why it's called the corresponding? It's associated with L sub y, right, the left-hand side. And then it's the homogeneous dE because we set the right-hand side to 0. Why this is important here is we can actually get a general solution, and we're not going to talk much about the theory of why. We can get a general solution of the non-homogeneous solution. Remember, that's when that right-hand side is not a 0, but it's a linear ODE. Well, I can get a general solution by first finding the homogeneous solution. That's the corresponding, that's what we were talking about over here, right? Taking your dE and setting the right-hand side to equal to 0 and solving. And we'll talk about these methods. We know none of them yet on how to solve. We're just talking about, we're going to work our way up, moving this left-handed side first being equal to 0. Then we're going to start making that right-hand side more and more complicated. This whole theory part at the beginning kind of gives us some foresight on what's coming up. We're going to want to find general solutions of non-homogeneous, meaning the right-handed side is not 0. And the theory tells us we can do that by taking the corresponding solution and adding it to a particular solution to the non-homogeneous. I don't have to find all solutions. I just have to find a particular solution to the non-homogeneous. That's typically where we're going to be starting eventually, like solve this dE where the right-hand side is not 0. All right, we are going to work our way up. We haven't even really covered this case much for a linear dE, besides a first order linear ODE. We can solve one of those, but above a first order, we haven't talked about it much. All right, so let's take this first example. This is going to feel like a silly example, and that's okay for right now. It says find the general solution of that dE, and they give us two things. They say this is the particular solution to this actual dE. If we were to use that solution, it will satisfy the dE given to us. This satisfies y double prime minus 6y prime plus 9y equals 0. That's the corresponding homogeneous solution. And the theory above that we didn't discuss, we're just going to accept it as it is, says the general solution to a non-homogeneous linear ODE, and we're going to work our way up to this, is I just take the particular solution and I add it to its corresponding solution. So y equals, and I literally just write all this stuff in, 2/3 x squared plus 8/9 x plus 2/3, and I add it to the other solution, C1 e 3x plus C2 x e to the 3x. All right, what we just found was the general solution to y double prime minus 6y prime plus 9y equals 6x squared plus 2. That is the magic that is going to be happening with this and what we're going to be working with. So the first thing we're going to do is work on solving the homogeneous case. The long-term result of what we're going to want to do is solve the non-homogeneous, meaning the right-hand side gets bigger than 0, right? It's not 0 in some way. It's not 0. What we're going to need in that way is we're going to need to first solve the corresponding homogeneous, meaning making the right-hand 0. It's a simpler case. Then we're going to use a method to find a known solution, a particular solution to the actual dE given, and then we can grab our general solution in the third step by just taking those two things and adding them together. All right, that is our global picture of where we're going. We first, though, need to work on solving our homogeneous case.